Welcome again. Today we look at the Gibbs free energy and its relationship with the equilibrium constant K, looking specifically at solving questions like this. But before we can begin to approach a question like this, it is important to get a better understanding of first the Gibbs free energy, and then to consider how it's related to the position of equilibrium of a reaction.
And what is the Gibbs free energy and why we study it? The Gibbs free energy, put as simply as possible, is a thermodynamic parameter to define spontaneity. A spontaneous process like this ball rolling down this hill is one that occurs without the input of energy from the outside, while a non-spontaneous process could be seen as this ball going up this hill. And here, energy would have to be provided from the outside to push the ball up the hill. But what about a specific chemical reaction to demonstrate spontaneity? Well, a great reaction to consider is the classic reaction between sodium and water, an explosive reaction that can provide you with a mini fireworks display here in your beaker. As the sodium reacts with the water, heat energy is released from the system to the surroundings. There's an enthalpy change where the system has lost some energy, and this can be summarized as saying that there is a negative enthalpy change, or that delta H is negative. But is this the only parameter that determines spontaneity? Should we say that once a reaction is exothermic, then it's automatically spontaneous? And the answer to that question is an emphatic no. In this particular reaction, we can consider the change in entropy, as sodium, which is in the solid state, and water in the liquid state react to produce sodium hydroxide solution. Then there is an increase in entropy, which put simply is an increase in disorder, or the system now has more ways of arranging itself. This increase in entropy, or the positive change in entropy, delta S, is also a parameter in determining whether a process is spontaneous or not. Of course, the reaction between sodium and water is indeed spontaneous, but it is exothermic, and it does take place with an increase in entropy. Reactions of this type are always spontaneous. Consider this block of ice being put here into this glass of water. As it begins to melt, the ice changes from the solid state into the liquid state. And as it does so, the ordered arrangement with limited motion in the solid state allows for more movement and more possible arrangements in the liquid state. And we say that the entropy change is positive when this happens. But as the ice melts and bonds are broken, energy from the surroundings needs to be taken in to allow this to happen. And the system itself, the block of ice that is, takes energy from the surroundings. And this positive uptake of energy by the system is defined as a positive enthalpy change. So if we have a positive enthalpy change and a positive entropy change, then we can have a spontaneous process, because the melting of this block of ice is surely spontaneous. Or is it? Ice would only melt at certain temperatures, temperatures above 0 degrees Celsius. So then, the process of this ice melting spontaneously is indeed dependent upon temperature. So it follows that whether a process is spontaneous or not depends on the enthalpy change, the entropy change, and temperature. And this is where the definition of the Gibbs free energy comes in. where the change in the Gibbs free energy, delta G, equals delta H minus T, the temperature in Kelvin, times delta S. And in the case of the melting block of ice at room temperature, delta G becomes negative. For any spontaneous process, delta G, the Gibbs free energy, is always negative. In this case, delta H, the enthalpy change, is positive, and we have an endothermic process. And delta S, the change in entropy, is also positive as solid goes to liquid. But it must be noted that this spontaneity only exists at room temperature. And if the temperature is cold enough or low enough, then the process would become non-spontaneous and the Gibbs free energy positive. If we consider the reverse, where we place a tray of liquid water in the refrigerator so that it could freeze and move from the liquid state into the solid state. As it does this, the freedom of movement in the liquid state becomes confined to the limits of a solid. And as this happens, we say that the change in entropy is a negative one. And as ice forms and the bonds are made, energy is released from the system into the surroundings. And because the energy is released from the system into the surroundings, the system loses energy, and we have a negative value for delta H, the enthalpy change. So here we have a case of a fall in entropy and an exothermic process. And when you have an exothermic process and a decrease in entropy, then you also have a spontaneous reaction with a delta G value that is negative. But once again, it should be noted that this is dependent on temperature, and only at certain temperatures would liquid water go into the solid state. So only at low temperatures would this scenario give a negative delta G. And if the temperature were higher, then this process would not be spontaneous, and we would have a positive value for delta G. So again, we see that delta G is a relationship that involves the enthalpy change, temperature, and the entropy change. Delta G is equal to delta H minus T delta S. And this mathematical expression for the Gibbs free energy is the best way to define what it is, because it is a measure which determines the spontaneity of a reaction, and it shows that this spontaneity is dependent upon whether the reaction is exothermic or not, whether the reaction takes place with an increase or a decrease in entropy, and of course, the temperature. Let's consider this table to summarize the examples considered in this lesson. First, we looked at the example of sodium reacting with water, a very strong exothermic process that took place with an increase in entropy. So here we had a negative value for delta H and also an increase in entropy. When we have this combination, delta G is always negative regardless of temperature, and the reaction always spontaneous. But then we looked at the case of the melting of ice, a process that requires the uptake of energy from the surroundings, and as such has a positive value for delta H as the system takes energy from the surroundings. But as the ice melts and goes from the ordered solid state into the liquid state, the entropy increases. So with this increase in delta H and this increase in entropy, we considered the melting of ice, which was a spontaneous process, as shown in this lesson. but it was only spontaneous because it was happening at room temperature, which is high enough. And once the temperature is high, then delta G would become negative and we would have a spontaneous process. But we must note that this combination is dependent on temperature, and we only get the negative delta G at high temperatures. Then we have the reverse case. As the liquid water freezes, we have an exothermic process as the system loses energy to the surroundings, and we have a decrease in entropy as the liquid organizes into the solid state. But this is only spontaneous in the freezer at low temperatures and positive at high temperatures. And finally, we have one combination that was not considered with an example, and this involves an endothermic process that takes place with a decrease in entropy. Such a process would always give a positive delta G and is never spontaneous. For any such cases, we can describe these reactions as spontaneous in the reverse direction. So we realize that as a reaction proceeds, the Gibbs free energy becomes more negative. And as the reaction proceeds towards products, an equilibrium could be established where beyond that equilibrium, the Gibbs free energy change becomes more positive. And when that happens, we can simply say that the reverse reaction is favored. So the Gibbs free energy change, therefore, is in some way related to the equilibrium process. And we express this relationship with this equation. Delta G is equal to negative RT, where R is the gas constant, T the temperature in Kelvin, and Ln is the natural log of K, the equilibrium constant. And with this relationship in mind, we now have a connection between Gibbs free energy and the equilibrium constant. And it will allow us to solve questions like this one.
Because we know the fixed relationship that exists between the equilibrium constant and the Gibbs free energy. And given the data for the Gibbs free energy, and given the data on the temperature, and given the fact that we know the gas constant, then all of these parameters can be plugged into this relationship, and then we can solve for ln K as shown here. And we can end up with this final value for the equilibrium constant of 2.42 by 10 to the power of 2.